So now we need to look at some different things that can happen. The simplest reaction you can have with enols and enolates is actually just the process of racemization. So the racemization is where you take something that is a chiral compound and then turn it into equal amounts of S and R isomers. So we've already drawn the keto-enol equilibria, and that's all we need to do here. So for the mechanism of this, I'll draw under basic conditions now, but it'll be an analogous process if we were to consider tautomerization under acidic conditions. And we can see how this process takes place, because even though hydroxide is not a very good base, these equilibria can be established quickly. And we see that upon deprotonation and formation of this enolate, we completely lose all of the stereochemical information that used to be on this carbon. It goes to a flat enolate. So now, whenever we go and reprotonate this molecule, it could go and be attacked by either the top face or the bottom face to give equal chances of making either one of these enantiomers. So a reminder, these would be enantiomers. And since there is no discrimination between faces, we would end up making racemates, which means equal amounts of either enantiomer. And this looks kind of boring. It's true. Since we didn't really change the molecule, we just lost some of its chiral information. But there are labeling experiments we can do which can be a bit more instructive into the reactivity. So this is an interesting problem where now we're essentially going to be undergoing keto-enol tautomerism, but now we're going to be changing the hydrogens into deuteriums. So we have all these deuteriums that for all intents and purposes react just like hydrogens. And we can see where these deuteriums get put into the molecule. So the goal is to write a mechanism. So I'm going to show you soon how to do this. If you want to stop and try for yourself, go ahead. So let's first talk about the hydrogens that are right next to the carbonyl. These end up being probably the most straightforward ones to see, because we already talked about how protons that are adjacent to a carbonyl compound or to a carbonyl group are quite acidic. So if we have our deuterium oxide, this can simply deprotonate this hydrogen to make a new enolate. And then it can react with water to do the exchange reaction and give us a monodeutyrated product. This can happen once again, now with this other hydrogen, to give two deuteriums alpha to that carbonyl. The next two I want to talk about are these bottom two. So these look very far away from the carbonyl, so you might think at first, why would those be acidic? Well, as we always say, this acidity of a hydrogen directly corresponds to the stability of the conjugate base. So we can have the same process, and we can deprotonate this hydrogen. We know that this can be deprotonated because we end up getting deuteriums there. So let's first localize this negative charge on this carbon. As you can see, we end up having actually multiple resonance structures for this enolate. You can put it on this neighboring carbon by moving the hydrogen of the double bond over, and we can further migrate this charge up to the oxygen. So we end up making what's called actually a dienolate, or it's an extended enolate. But as soon as we deprotonate this hydrogen, it is already in resonance with this carbonyl system, and really the charge is shared between this carbon, and this oxygen. Now if we imagine this enolate Coming back, we have deuterium. We attack this. Now we can install the deuterium right here. And again, another deprotonation would put it again in that same place. But turns out we wouldn't necessarily need to go all the way through the molecule. I'm going to copy this same intermediate we just had, and let's take another look at it. So as we mentioned, we end up having also negative charge on this carbon. So in addition to protonating all the way at the end, you could also have it directly react at this next hydrogen, or at this next carbon. And you could end up making a deuterium here. Note that along the way, this hydrogen that is neighboring to the new deuterium is still acidic. So we could have another deuterium. Another deuterium oxide, attack this hydrogen, go down, and back up. And once it does this, now it's able to eventually attack back we have the deuterium in the place we observe in the product up here in this last position. And this could keep reacting now at the most distal carbon to make the reaction product observed. Overall, thermodynamically, this double bond will want to be in conjugation with the carbonyl, so we wouldn't likely expect to see much of this type of intermediate as a major product after the reaction. Oops, caught myself writing hydroxide again. So while that is perhaps a bit mundane, we can actually start to introduce new groups using these reactive enolates, particularly with different types of electrophiles. So the first electrophile we're going to see here is bromine. And we see that we can actually go and introduce the bromine in this alpha position. And if we started with a chiral starting material, we would end up with a racemic mixture. So we're going to have the same process where hydroxide will deprotonate the alpha hydrogen. We'll go to make our enolate. And enolates primarily react at the carbons. So whereas we can make some of the etyl tautomer with protonations, almost all electrophiles will be reacting with enolates at the carbon center. This has to do with the frontier orbitals, which if we had more class periods, I would teach. But for now, we just want to keep this generally in mind, and this will be a consistent trend throughout the class for the rest, where these types of enolates will be reacting on the carbon atom. So we can have a direct attack on this bromine, and this will lead us to either of the two brominated products. Not so bad. Again, you could be going through the enol intermediate as well. This would look very similar. We would use the acid-base tautomerization chemistry to get us now to a flat enol form. And we already know that double bonds react with bromine readily, and enols can react with bromine as well. You can draw this as the enol directly attacking the bromine to give a protonated carbonyl intermediate first. Methyl. And the bromide anion will be able to deprotonate this hydrogen to regenerate the acid to make the product. Potentially, you could also draw a bromonium forming here. That would also be acceptable. But due to the strain of the bromonium, the lone pair on the oxygen would likely come down and ring open this ring to give you this intermediate. So if you want to draw bromonium followed by ring opening, that'd be fine. Or you can just go directly by using the lone pair on the oxygen to add directly to attack the bromine directly. So it turns out if you have more than one alpha hydrogen on next to your carbonyl, these can continue to keep on reacting. So we're going to go through the same deprotonation halogenation process. Each time you add on a bromine, the alpha hydrogens get more acidic, so they're even more readily deprotonated to continue reacting with bromine until you end up with a tribromoketone. So these can continue to happen over and over again. And once you get to a trihalogenated methyl ketone, something crazy happens. Turns out the sodium hydroxide no longer acts as a base, it can actually substitute this entire group. So that means that because of the electron deficient nature of these bromines, this entire thing becomes a good leaving group. So this will proceed in a manner that we've seen like all of the other substitutions take place. So I'm just going to shortcut to this Br3. Now the hydroxide has nothing else to deprotonate. It can attack the carbonyl. We would go to a tetrahedral intermediate. And the tribromomethyl anion is actually quite stable. So we briefly make a carboxylic acid that gets deprotonated in other reaction conditions, along with the tribromomethyl anion. You could do this with different sort of iodine electrophiles or chlorine electrophiles. Overall, this is called a haloform reaction. So haloform, halo coming from halogen. Form is usually abbreviation for a single carbon atom. So things like chloroform, bromoform, and iodoform are the names, common names, of all of the trihalogenated methanes. And this is a fairly interesting and non-obvious way to turn a methyl ketone into a carboxylic acid derivative.